Hey, what up, people? Yes, I'm having another stream today. I had one earlier on Agree to Argue. It was on slavery, and I was with like Dr. Josh and Dr. Fuzz Rana. But today I got a different doctor on for a different subject entirely. Yeah, I mean, way out of left field on this particular topic. And that's when I might perk up and go, yeah, this is going to be awesome because I love this topic. And Dr. Kroon, my friend, my buddy, my awesome pal that knows this material like the back of his hand, said, hey, I want to come on your channel and talk about how to go faster than the speed of light with not using warp stuff. And I'm like, let's do it. So anyways, I'm very caffeinated today, as you can tell. But John, what's up, buddy? It's been a while.
What's up, everybody? Yes, but Steve, it's not faster than light, but it's definitely exploiting all that special relativity has to offer. And I believe very few science fiction movie writers and so forth and creators have actually exploited or tapped into this very untapped resource. And so it's just a point of contention for me as an avid science fiction viewer. As a physicist, it's fun to watch movies and stuff, and but I wish they would put more stuff like this in there. That's
Yeah, no, I
all
think
I
that's
have to say
awesome.
about it.
I've read a lot of those books back when I was a kid, right? I mean, I grew up with things like Star Trek, and I used to read a lot of science fiction books that dived into these topics, and even nonfiction too, like a lot of Penrose stuff and Paul Davies and a few other things. So there's a lot of different theories back when. Hey, how are we going to get to the stars? And if we do go to the stars, is there what's the limitations we have to overcome, right? And so you kind of have been thinking about how we can actually do it. That's very practical and productive even. I mean, something that theoretically could be done now if we wanted to, right?
Yeah, so the idea is within our current lifetimes, I foresee that it would be technologically feasible to achieve something similar to what I'm going to talk about here. And the cool thing about it, it doesn't require anything fancy or weird like negative energy, whatever that is, or exotic forms of matter, or these mythical dilithium crystals and so forth. It's just you just need a very potent source of energy, such as nuclear fusion, which, despite what you may have heard, is actually maturing pretty quickly. And I'm pretty confident in my lifetime, probably in the next decade or two, we'll see some early generations of a perfected draft one nuclear fusion coming online, and they're so powerful and pretty safe. You could actually retrofit one to a spacecraft, and we're going to talk about what that buys you, what the positive consequences are here.
Cheshire sends her love and adoration, and she's fawning over you. Apparently,
she still remembers that
if you're
seafood
single,
pasta.
if you're available, if you're going to be in Canada any near future, whatever.
Well, note to self, but I'm sure she remembers my seafood pasta dish that I explained and described.
She might. No, she actually might. But yeah, maybe you guys should do some cooking stuff together. So let's kind of dive into it. And by the way, I think fusion should have been around a long time ago. I think fusion is much safer. It's just, you're dealing with thermal temperatures that are quite astronomically high. But as far as like the radiological considerations, they're nothing compared to fission. So yeah, I don't know why we haven't invested in more fusion. I mean, we've had fusion reactors that work. We know they work, and I think that we can have something that's sustainable. But we just don't seem as a country to want to get into those types of energy markets for some reason. I don't know why. It seems odd. You think that if we could develop fusion on a large scale, and we could solve pretty much world problems for energy consumption. I mean, we're not going to run out of hydrogen. I can guarantee you that's not going to happen.
Yeah. And one quick note. Right now, artificial intelligence, like full-blown AI, we're about as close to rolling that out as we are to fusion. And right now it's a race. If AI gets here first, we could literally just ask it, calculate this and print out the blueprints for a fully functional,
awesome.
perfect. And so then it wouldn't matter how far off we were from fusion. Like AI is much easier. Well, don't quote me on that, but it's definitely happening much more quickly than fusion.
Yeah, no, I think we're definitely in agreement there. All right, so what do you got for us? How are you going to show people the special relativity here?
Okay, so I have this one note here on my tablet. Pardon my penmanship because it's a little bit finicky, but I would like to start out with a simple derivation of the Lorentz factor because I think it's really elegant and very visually appealing using some geometric shapes and drawings and whatnot. And then I'm going to derive the hyperbolic motion through Minkowski space-time, and the consequences of that will be apparent to you by the time the derivation is done. And then we'll look at some tables and calculations. But before I start doing derivations, I would like to just say, in order to motivate this derivation, I will tell you that you can kill two birds with one stone. And with this approach I'm going to be presenting, this hypothetical fusion-based technology, propulsion technology. By the way, the fusion reactor is going to be more than strong enough to produce force fields. We have force fields now. It's not futuristic, just a really strong magnetic field. That'll get rid of pretty much any charged particles. And then you turn to material science with really lightweight, high cross-section materials that block out neutron and gamma ray and X-ray radiation. So you're clear, you're good to go interstellar or intergalactic on the radiation front. You can grow food hydroponically. You can scoop up hydrogen. You're literally plowing through the ISM, hopefully sufficiently low density to not cause problems on your momentum. But you can literally have access to like pretty much limitless fuel that your fusion reactor
you scoop it, right?
Just scoop, yeah.
Mm-hmm.
And so there are two very big problems, bigger than the food and water and recycled air and radiation protection, that are what people go to immediately whenever you say, oh, let's go interstellar. The first is time. And the second, are you going to be able to have a long enough human lifetime to get across the galaxy or even to the nearest planet outside of our solar system? And are you going to have problems with bone loss, bone density, and heart weakening? I mean, the ISS astronauts, even just within 6 weeks or a couple months, they come back and need intense PT for a long time. And we're talking about potentially years. So I'm going to solve both of those problems with one single solution. And but hold on to that thought. I'm going to start with the derivation of the Lorentz factor and what is known as the light clock, in which you have a mirror. There's a simple mirror that bounces a photon up and down. So you just have a photon, it goes up and down, and such that the one complete circuit up and then back is 1 second. So it's 150,000 kilometers between these two perfect mirrors. The photon will never decay away or attenuate. And so you have a light clock. It's called a light
These are perfect
clock,
reflectors, right? Okay.
Yeah, light clock. All right, so now imagine that this clock is moving with speed v. It's just two parallel mirrors, and they are at a fixed position, somehow held in that location, in that orientation, maybe inside a ship. And it's just a clock, and you can watch it, and you could time the number of ticks that the photon bounces back and forth. And so as this thing moves at different intervals of time, you'll notice that it actually ends up, so I'm going to get rid of this real quick, tracing out a different shape. It goes bounce, bounce, and so on, and so forth. And so let's call this remember, one bounce to one bounce is still, when it comes back to the bottom mirror, that's still 1 second, because that's how we've calibrated it in the first place. But you'll notice that the distance from just one mirror to the other and then back again is, just by geometrical considerations, shorter than these two hypotenusae of this implied double-sided right triangle. Do you agree, Steve?
Absolutely, yeah, because you're now moving along the y-axis rather than just up and down the x-axis.
Absolutely.
Right.
So we're going to have the following time designations. Greek letter tau is proper time. So that's like the time in your rest frame as you watch this thing flying by. And then T prime is the a dilated time inside the spaceship. And so pretty much it's just Pythagoreans theorem. We have this distance here. This leg is L equals c tau over 2. Stay with me here on that. The reason why it's over 2 is because from here to here is 1 period. Well, we've only gone halfway across, so that's half of that period. And then we have c t prime over 2 here. And then this distance here along the length, that's the speed of the ship times t prime over 2. So now we could square all these and use the good old-fashioned Pythagoreans theorem. We get c t prime quantity squared over 2 equals vt prime over 2 squared plus L squared. And just to do this a little bit quickly for you, we have L squared equals c t prime over 2. I'm trying to write fast and my penmanship suffers. Vt prime over 2 squared. I'm going to factor out the t prime squared over 4 and substitute L is c tau squared over 2 and square that. So we just get a t prime squared over 4 and a c squared minus a v squared. So the factors of 4 cancel. I'm going to divide by c squared and actually square root both sides and then rearrange it. So we end up getting t prime is tau over square root of 1 minus v squared over c squared.
Which is the standard Lorentz contraction formula.
Yeah, and gamma is just that bottom factor, v squared over c squared. And so we could say a dilated time is equal to gamma tau. Or we could say tau is equal to, whoops, I did that backwards, sorry. So it's t prime is tau over gamma. Forget about that, tau over gamma. Because tau is the proper time and you reduce it by the way, gamma is always greater than or equal to 1. So we're reducing the proper time down, that's time dilation. So if you put in like 1,000 years into here and gamma is really large, then t prime on board the spaceship could be conceivably pretty low. So so if I did that correctly.
So as the denominator gets higher, the amount of time dilation is going to be more notable.
Yeah, I should draw a graph. So here's v over c, and then this is equal to 1. There's a vertical asymptote. Here's gamma, and it starts out at 1, and it doesn't do much until you get really close to v over c equals 1. It just goes, it diverges. It's an vertical asymptote. So that's pretty interesting, and we're going to see some of the consequences of that tonight. So that's the first part of the derivation, but I'd like to move on now to the next part, in which I look at accelerated motion. It's a common misconception that special relativity can only treat uniform constant motion, but really that's not true. You could deal with forces, which involve accelerations, and the 4 acceleration. You can look at the 0th component to get the regular 3 acceleration, and so forth. And we deal with this all the time. Momentum transformations and impulse. The full spectrum of classical Newtonian mechanics can be dealt with in a relativistic sense, and these involve accelerations. We're going to actually make use of basic integral calculus to help us with this. So I'm going to start off with just a basic textbook equation. AC is v over t prime. So AC is, well, t prime is the one from above. It's the dilated time interval that elapses in the visited inertial frame. At the instant speed v is reached after AC, which stands for constant acceleration, measured in the acceleration frame. So I know it's a mouthful, but speed v, t prime is on board the ship, and AC is the constant acceleration in the ship frame. And so we have, we could rearrange this and just say t prime equals v over AC. And we also know that we have I'm going to introduce yet another t. I'm really sorry, but it's going to be capital T sub u, which I'm going to define as t prime over tau. Now this might look like 1 over gamma, and it kind of is, but it only by proxy. It's essentially a result of the fact that the ship is constantly changing reference frames. Remember in college SR class, you learn about just a single reference frame that's moving at a constant speed, and you deal with your Lorentz factors and do a transformation and stuff. But think of acceleration as just a series of infinitesimal slices of time, almost like a movie reel. In some ways, I think of real life as a movie reel, only with a delta t equal to the Planck time. But this goes even deeper than that because it's a mathematical construct. So imagine that this ship is constantly changing into a higher boosted reference frame as it accelerates. And so because of that, and remember, we start at speed v equals 0 in both frames, and so everything's regular, everything's matched up. Then you hit the gas pedal and you start accelerating with your fusion drive. And so the accelerating frame cannot be just t prime, because the t prime is for just that instantaneous like time dilation factor. Tau is, of course, the proper time. So we have to have yet another time, t capital T sub u, which is essentially a value which is less than the time interval tau, but greater than the inertial frame time t prime visited at that instant. So we got tu, we're going to be working in this term. We're going to plug equation 2. What's equation 2? Oh yeah, 2 is just this one.
Do you think it's, if people want to really learn this stuff, do you think that they just even start with like the kinematics of the relationship between like velocity and acceleration for displacement?
Oh yeah, you definitely need that. Well, that's a prerequisite. If you don't have that, you got to stop, do that, and come back.
Okay, I know we're jumping really ahead for a lot of the most of the people in the audience probably this is pretty familiar with, but for those who don't, just to kind of help them out, you might want to review what velocity and acceleration are with respect to displacement, first and second derivatives, and things of that nature in kinematics. But as John's pointing out, that's kind of a prerequisite for a lot of this stuff, I think.
Yeah, it'll get better. Just trust me. I'm gonna prove this proof, and then we're gonna see how freaking awesome what it causes. All right. So I've just, while you were talking, I just said I plug this t prime into here, and so tu becomes v over ac tau. And now what I'm gonna do is remind you that t prime is tau over gamma, and v equals ac times t prime. And so I'm going to combine those to give, so this is like equation 4, and then equation 5 is v equals ac tau over gamma, which equals ac, just trust me, ac tau 1 minus v squared over c squared. Because 1 over gamma, that's usually 1 over square root, now it's in the numerator. And we're going to actually solve for v, this part, and this part. So v equals this times square root. There's a v squared and a square root sign, but we could square both sides, combine the v squareds after the radical is gone, and it's really cool. I'm just going to skip the algebra, and I'm going to show you that you get v equals ac tau over square root of 1 plus ac tau over c quantity squared. And this actually is on the Einstein poster on my wall behind me. It actually, well, a form of it is there. It's slightly different, but we have the 1 plus ac tau over c quantity squared in the radical in the denominator. So v is the instantaneous speed reached after time tau while accelerating at constant rate ac. And recall that equation 4 says that t sub u is, well, it's just right here actually. T sub u is v over ac t. So we have v equals t sub u, I'm just rearranging, times ac tau, and I'm going to plug that into this equation here, and we get, sorry, we actually have another t. This is tu prime, which in this case, it really should say t differential. It really should look like this, like dt tu, but it's a parameterized variable, so I'm not going to give it a differential preface. So tu prime is equal to 1 over square root of 1 plus ac tau over c squared. And this represents the constantly changing elapsed accelerated time t sub u. It's almost like a differential t sub u, like I said a minute ago. And so now we're actually going to integrate, noting that the integral of tu prime by definition is t sub u. So in a sense, tu prime is sort of like I said earlier, dt sub u. So we're going to integrate both sides of this from 0 to s. S is, we'll see in a minute. We're going to get t sub a is equal to the integral from 0 to s of tu prime d tau, which is equal to integral from 0 to s d tau of the square root of 1 plus ac tau over c squared. Now s is the elapsed time, the total elapsed time since tau equals 0 in the stationary frame when t prime also equaled 0. It's the total time measured from Earth. And when you do this integral, it's actually pretty straightforward. You just get an arccinch. So for example, like if you have 1 over square root of 1 plus x squared dx, that's just hyperbolic arc sine x. There you go, Steve.
You know what? The only reason I remember that is I actually did something very similar on Twitter not too long ago to show somebody where I got something as the arc signage.
And if there's like an a over b factor in there, then it pops out due to u substitution as b over a out front overall. So, all right, forget about that. That's just a little. Yeah,
nobody ever memorizes these integration formulas. Everybody goes to a table when you need them.
Yeah.
I'm sure you have a lot of them memorized, but I never bother.
Well, I could derive them if I forget them, especially if I'm in traffic. ACS over C, and then the 0 arc cinch of 0 is 0, so it's trivial. So we're just left with the upper limit. And so this right here is really important. This is what we're going to actually analyze now in Mathematica. And I'm going to show you some plots which are going to help bring this home for you. So I just have a simple Mathematica spreadsheet here. I define the speed of light in meters per second. I have a little conversion factor, the number of meters in light years, not kilometers. And I have some scripts here. It calculates this thing called TS, which is actually S in the other notation. And then I have the acceleration time in years, in which I input the total number of light years you want to travel and the acceleration rate that you are going to undergo. Now, before I look at this any further, let me just come back here. This is one of the take-home points. Remember when I told you your bones decay and your heart weakens and all that stuff after just a few weeks, and we're talking about potentially years in space? That does not apply. And a lot of science fiction authors try to have like some doohickey that's spinning around, and you have other problems whenever you try to create artificial gravity from circular motion. A lot of mechanical problems, and it's dangerous. More things are likely to break, and you get dizzy, and you got to be hopped up on Dramamine all the time. And so it's not good. And there are like pseudo forces that can arise, like Coriolis-like forces and centrifugal forces and all that jazz. So you want to try to avoid a circular motion. But what's cool is the rocket. Here's Earth, and here's your rocket. Okay, and it's going in this direction to some star with a planet going around it, and you're going at speed v instantaneously. V of t is naively, and the classical case is just your acceleration times time plus some v naught, right? So you're in orbit, and then you launch out of there, and you go on your journey to Proxima Centauri or something.
Sure.
Forget about the vector. So if you accelerate, if a equals 1g, well, guess what? You're good. The bone problem, the heart problem. Like your health is great. You can maintain muscle mass. You just have it so that the floor plans have it so that you're all sort of like standing like this, and you feel an apparent force of gravity. Einstein's equivalence principle of 1g feels just like being on Earth. Here's another idea. Check this out. What if you're going to like Kepler 22b or something, and it's like 1,500 light years away, and last estimates put its surface gravity at like 1.8, and some other ones more like 2.5g. Well, you wouldn't want to get that. You wouldn't want to go at 1g and then get there and be all weak. What if you actually accelerate there at whatever surface gravity the planet has that you're going to? Maybe 2g. Granted, 2g might be feeling a bit rough during the journey, but you'd be surprised how remarkably adaptable the human body is. Or you can have your acceleration change. You could just start out at like 1.3g and then slowly, like the frog in boiling water who doesn't really notice the slow changes. By the time you get to your destination, your muscles are stronger and bigger, your bones are denser, your heart is stronger, your blood vessels, all that. You get there and it feels just like being on Earth. But if you hadn't undergone that conditioning for years and years, you would get there and probably break a leg just holding yourself up. Here's the cool thing: you get
to it.
Right, but you would want to make sure. You mean on the rocket? Yeah, you'd be
acclimating as you're traveling.
As you're going there. Now let's look at some of these numbers. This is really cool. So I've only done the calculations for one.
A quick question: If I'm accelerating, according to the equivalence principle for Einstein, of course, you can't tell the difference between acceleration and gravity due to mass, right? But if I'm accelerating at a constant rate, that means I'm going to be going faster and faster and faster, correct? Mm-hmm. As you get closer.
Yeah.
Yeah. Okay.
Well, up until you become like ultra relativistic, then you have relativistic effects. But in the ship frame, your acceleration is always the same; it's a constant.
Right.
But people on Earth would be like, "Oh, they're not. Their speed isn't changing per unit time like it used to be, but they're also like almost frozen in time. They're like super time dilated." So you have all these things going on.
Yep.
So I've made this table in your honor called Steve McRae example, and I've made a table that shows on the x-axis the number of light years. I hope I labeled this thing right. Yeah, I labeled it right. So the number of light years you've traveled from Earth, and on the y-axis the elapsed perceived integrated total time in years that you experienced on the ship. And I go in steps of 10,000 just because I'm going out from 100 light years out to Andromeda Galaxy, 2.5 million light years away. Look at this, at 2.5 million light years away, you're just shy of 15 years. Like what? 15 years, and that's at 1G. If we want to do like 1.5G, and all I do is type this in, I could change that, replot it, and now it's looking like 12 years, for just a small increase in the acceleration rate. And this is perceived total elapsed time by the people on board the ship. So they would literally need 15 years of food and water and air and protection from radiation. And you have to make sure that the ship is constantly putting out that amount of force that is required to keep, even in relativistic regimes, keep that acceleration. Now, if you have to stop accelerating and fix something and it takes a week, okay, big whoop, who cares? You're going to still be getting, pretty much anywhere in the universe in a human lifetime. So I wanted to show you, I wanted to bring one more thing to your attention. You don't want to just accelerate and accelerate and accelerate and capitalize on all of the time dilation. Because when you get to your destination, you're going to fly past it at almost the speed of light, and you're not going to slow down nearly enough time. So what you do, you just, halfway to your journey, you turn around, you just do a spin flip, right? And you
do a negative acceleration burn.
Yeah, and you don't notice anything different. You're still moving this way, but now your acceleration is zero. Or less than zero, it's negative. So it'd be like negative 9.8 instead of positive. And so it's the same exact thing. The engines are still, kicking butt, pushing out all this energy. and you're still reaping the benefits of being in a perceived gravitational field. And then you time it right, so when you're halfway there, you flip, and then you don't fly past your target. Now, it's going to cost you a little bit in time, but not nearly as much as if there were no such thing as relativity. If there was no such thing as time dilation and whatnot, and you could just go any speed less than c, and you want to get 100,000 light years away, it's going to take you more than 100,000 years, because you're not going max speed the whole time. You have to ramp up your speed. But because so it turns out, like, roughly the first year of the acceleration, you're going in a way that your Lorentz factor, your time dilation factor, is not very impressive. It's relativistic, but it's like 1.4 or maybe 1.8.
What percentage of the speed of light would that be approximately? Because you really don't start noticing it about what, 20%?
So, no, more like 80%.
80%? Okay, well, okay, we shouldn't notice, but I mean, correct me if I'm wrong, but
well, I mean, depends on what
satellites have to take into account, and they're not going 80% the speed of light.
So, right.
What's that?
So yeah, if I want to do a quick calculation here to remind myself, yeah. So even at 84% the speed. Whoops, sorry. Hold on. Let me fix that. -1/2. Yeah. So at 84% the speed of light, you're still less than a factor of 2 time dilated. For human purposes, that's okay. Okay. But yeah, for satellites, yeah, you definitely. Yes.
But for us, yeah, until you're going around 80%, give or take, at speed of light, and who cares, right?
Mm-hmm.
Okay, works for me.
All right, so check this out. I'm going to show you. So we looked at this this graph here, and so this is light years. Look, 2.5 million light years. We're talking about a little over a decade. Okay, remember, that's for just accelerating the whole way. Now, I've reminded us of this caveat where you need to turn around halfway and start decelerating. So actually, I decided to put everything into a table form. So the top table has the destination, the distance in light years, the time elapsed in Earth years, and then the ship time. And so look, you can get to the edge of the observable universe where it is right now, about 13.8 or 9 billion light years away. It would take you 23 years. You can get anywhere in the universe in 2 decades. Like, what? Okay, now, so you can't stop at your destination when you fly by it at the speed of light, almost. So you got to look at this second table. So it's almost double the time, but still you're not doing too bad. Proxima Centauri, you get there in 3.56 years. Anywhere in the Milky Way, like 100,000 light year diameter or more, 100,000 light years would take you 22.4 years, and you're not flying by your target. We're talking orbital insertion alert. And then all the way, look at this, just 5 more years to get to the Andromeda galaxy.
Now, how does it factor in that, because you still have proper time happening, Andromeda is moving towards the Milky Way, right? So even though it would be to your time, your local time, only less than 30 years, how would that? How's the fact that the Andromeda galaxy is moving toward us at a pretty noticeable rate calculate to that? When you plan ahead of you and say, look, I'm going to get there in this amount of time, proper time, does it make a difference?
No, not. I mean, sure. I mean, it'll shave like a couple months off, but I mean, it's not moving relativistically, of course. It's
but you're still going to factor that in.
It's slated to right. So it's slated to start merging with the Milky Way in about 4 billion years. In Earth time, our spaceship, even traveling almost the speed of light, would take about 2.5 million years to go, 2.5 million light years. But it would still take only 28.6 years from our point of view. So maybe this would be like a 28.2 or something. Gotcha, okay. If you take into account. I mean, every little bit helps, so that's pretty cool. And the most extreme case, 45.3 years. That's like, that's a bit long. That's like your whole natural life. But if
somebody says, "Hey, look, I want to be sent to the edge of the universe," it's not. It's something that actually be, done. It actually can be done in theory, correct?
Yeah. And so, but think about that. Even just our own galaxy, there are billions and billions of planets. There's a lot of them are within only 1,000 or so, or a few thousand light years. If you look at the Kepler data, let's actually look at that. Let's see here. How long would it take you to get somewhere That's 1,000 light years away. Here, just 1,000 light years. Oh, come on, that's easy. 7.4 years. If you want to blow past it, and if you want to actually stop and not be flying almost the speed of light when you get there, it'd be about 13 and a half years, and that's at 1G. If you're going to like Kepler 22b, let's do 1.8 Gs, and let's just say you can withstand that, or else they ease you into it. So that total of 8 years, including the fact that you got to stop and start slowing down halfway, 8 years to go 1,000 light years at 1.8 G of accelerate. That's 8 years. I mean, sure, most movies it's like, oh, they could barely make it to Mars, and they're going crazy and start, having psychological problems, and they make some cool movies out of it. And that's a valid point. You might want some sort of like holodeck, or maybe you do want to do some basic cryo sleep for part of it. But you could do it without any cryo sleep. You could just live your life, tend to the ship, make hobbies, fix stuff, plan what you're going to do when you're there. There's a lot of work to do on the ship. Look out at the stars, do some astrophotography from a Bortle like 0. What that would be doesn't even exist, but with no light pollution, you turn off the ship's lights, and you're in a Bortle 1. And just the possibilities are endless. I didn't need to invoke some fictional negative energy or wormholes or time travel or anything funky, like stuff that it's just an engineering problem. Like, so we get the fusion drive online. After the fusion reactor technology is perfected, AI will probably be online before we, on our own merit, perfect an actual fusion reactor. But again, it's sort of like a race. I'm not sure which one will happen first. We retrofit it into a spaceship, and there are many different ways you could use ion drive or just directed energy. You can have that power all of your water and air recycling systems, your defense systems. You could have like what they use at CERN. And when I was working over there at CERN, at the LHC, you have cryogenically cooled coils, like solenoids, where you could produce really strong dipole magnetic fields, and with other magnets you could create octupoles, and you're running like thousands and thousands of amps through these wires with essentially zero electrical resistance loss, no loss of energy, because they're in a superconducting state, and so you can create super powerful magnetic fields in as large as you want them, really. And any charged particles that are either flying through space relative to the center of mass of the galaxy, or they're just sort of sitting there floating in the disk of the galaxy, and you plow through it at almost the speed of light, it's going to experience a strong Lorentz force, which will just pretty much deflect it around your ship. And then again, a little bit less my territory, but material science. I've seen some articles lately, and I have some friends even working for the Army developing some cool stuff, in which we have these like aerogel type materials that are like almost weightless, like almost zero mass, which is good for a spaceship, so you don't have as much of an energy expenditure. But they're doped with high cross-section material, almost like having lead in there, except for it's not lead, it's almost lightweight, and it'll absorb your ionized, so like radiation that doesn't have a charge, your neutrons and your gamma rays and X-rays. You could even have like a layer of water ice in there. I think there's actually a movie. I know it's called A New Life. It's a TV show on Netflix, and they're coming back from like Mars, from Jupiter, and they actually have like the hull. I don't know how realistic this is because water's pretty heavy, but not as heavy as metals. But there's like this layer of water or water ice in there for the neutron absorption.
That's actually what I had to study, believe it or not, was macroscopic cross-sections for absorption in boron material and doping for fuel rods, right, for the reactor core systems. So you're right there. You're just kind of speaking my language because I know exactly what it refers to. Scattering and a few other things. So yeah. So what people may want to realize is what he's talking about is that you have what's called a Barn ratio, right? So a barn is an average. Was going to be like the target to something. So if you have a bigger target, a parent target, then it's more likely to be absorbed. So if you have a neutron coming into a fissile material, if it has a hard Barn ratio, it's going to absorb that neutron and not let it pass, right? So you have an absorbing factor because neutron radiation is bad for you. It's really bad for you. It's like 20 times any kind of non-ionizing or electromagnetic radiation. So what he was suggesting is having some kind of gel that has some kind of a doping agent in it that will help alleviate some of the problems for radiation. Now, I don't have an issue with that. The problem is I think that the gamma and X-rays in outer space might be a lot more difficult to ward against. But these are all, like you said, material constraints, not physics restraints as far as like the actual travel.
Yeah, you can have pretty much like the Hall B detector on the Class 12 JLab accelerator facility where they actually, I worked on this. They have it's an electromagnetic calorimeter for these particles, and you have a high Z material and then organic doped plastic and layers of layer.
That's how it would have to be. I think it would have to be like a layer system where you have different materials and different things, and that would have an overall effect to minimize radiation. Because the only three factors in radiation I'm talking my outside chat right now, by the way, is that time, distance, and shielding. So how long you're exposed, the distance you are away from the source, and the shielding you have between you and the source. Those are your factors. So if you can minimize your exposure by having more shielding, then you've dropped your exposure quite a bit because radiation is bad for you. Let's put it that way.
So, Steve, what if you think of it like this? Imagine somehow harnessing the energy in the form of heat or electric current and powering auxiliary systems.
Yeah, of course. Yeah, well, that almost have to be a necessity because obviously you're going to have heat dissipation issues, right? So if you can harness that energy in thermocouples to utilize that heat dissipation as a form of secondary energy, that's basically a lot of things in space travel anyways uses a system very similar to that. So yeah, that would be very efficient. So you would one, be minimizing the radiological damage by having more shielding, and two, you would be able to take the thermal effects from that and be able to utilize it for secondary systems.
Yeah, it'd be freaking awesome.
Yeah.
So I'm just gonna really quickly on the fly here change. Actually, these become so clear contents. How do you clear? I just had delete. So I'm gonna do it for 1.8G real quick, and you could just chat about what you think about all this stuff. So this is, I sort of ran through the derivation because I wanted to. I didn't want to spend too much time boring people, but I definitely wanted to present it, and hopefully you all have enjoyed the consequences.
Yeah, they're thrilled so far outside. They seem to be enjoying it.
Yeah, so 1.8. So yeah, only 2.4 years instead of 3.56. And then for 100,000 light years, so we can get, and we're already at like 2/3 of the way out. So really, we can get pretty much anywhere in the Milky Way without even going that whole 100,000 light years. So now it's only 13 years, point something. The Andromeda galaxy, and there's probably all kinds of planets in that thing. 2.5 million light years and closing. And there's also the Triangulum galaxy just next to it, about 2.7 million light years away. So this is, what does it say, 16.5? Yeah, 16.5 years. Now, okay, I should have mentioned this earlier, but so when you're traveling this far, like billions of years or millions of years are actually, for the case of the Andromeda galaxy, you'll be gone like 2.5 million years each way. And if you spend any time there before you come back, then everyone you know, and their great ancestors or descendants rather are going to be long gone. So you have to go on this trip realizing that everyone you care about is either made peace with the fact that you're leaving forever, or you bring them with you. Maybe you bring all your buddies and your girlfriend and all your homies and whatever on the ship with you, and you go off to a new Earth, a far off land, and have exciting lifetime spreading throughout the galaxy, throughout the universe, potentially. And so even if you had warp drive, though, let's just pretend, for example, you can go like many thousands of times the speed of light and get to any planet and this sector of the galaxy. And the warp technology alone does not necessarily mean or guarantee, because they're completely unrelated, any quote subspace, how they say subspace frequency. So they're trying to say that they're emitting a signal to communicate with Starfleet or someone back on Earth. It travels as an EM wave through space to the nearest, and they're usually very near, a subspace transponder, and it converts that EM signal to some quantum entangled state that goes underneath the universe, like in zero. You know how you have like matter and antimatter? Some scientists think that there's regular space and anti-space, and some authors call it like zero space or Z space or subspace. And it just travels like at effectively infinite speed, because there's no space there. There's no special relativity laws to adhere to, and it just like flies through there really fast. Intact information packet picked up by the next subspace transceiver, converted to an EM signal like in Earth orbit, and just pings it almost instantly down to, and then you get the so warp drive has nothing to do with that, and that stuff might not even be possible, and especially maybe not even like technologically feasible, even if the physics and theory says it's possible. So we have warp drive. You get across like this quadrant of the galaxy, you're 1,000 or so many thousands of light years away, and you're like, all right, cool, I did that in literally 5 months. Like 5 months for me and 5 months back on Earth. Everyone's still there. They're going to Wegmans. Everyone's cool. Well, if you send a signal back with the comparatively slow speed of light, then they're going to still like be long dead by the time they get the signal. Not to mention, it better be beamed, because the 1/r² law says that it's going to reach like background radiation noise levels after just a dozen light years. Forget 3,000 light years. You better beam the hell out of it and hope that you've aimed perfectly.
So you want to have a beam, so you have less attenuation, and you want to have directionality, right? I would imagine.
Yeah, but you better pinpoint it and hope that nothing gets in the way. You
Good
hit
luck
some
with that.
star.
Real quick, Kawasa 10,001. Thank you, Kawasa. He just seems to be enjoying the conversation.
Oh, great! Thank you.
Yeah, so communication, effectively communication is not going to be applicable here. I mean, you're not going to be able to communicate with Earth, but if you decided to go to the edge of the observable universe, and we can get into like, can you even go past that, because space is obviously expanding, which would be problematic. You can't go fast. You can't. I don't know how you would go faster than that if space is actually expanding. But if you came back to where the Earth was positionally wise with respect to some frame of reference that you had, it wouldn't be there, right? The sun would have burned out by then.
Yeah, it'd be gone. And maybe have you heard about the Voyager conjecture? The Voyager conjecture says if you can get there slower than 50 years, don't go at all, because of a probabilistic argument in which at the rate in which we're discovering things and improving our technology.
We'll find a better way to get there.
And so by the time the Voyager space probes will be effectively at the distance that Alpha Centauri is for us, just in a different direction, in 30,000 years. So arguably, we're going to have something much faster, either what I'm talking about now or warp drive draw. Long before it gets.
They've had this theory to get to Proxima Centauri with probes in a matter of like a decade or something, right?
Well, yeah, that's Project Lightshot. I'm talking about like manned stuff. Yeah, Lightshot can get you there, get these little probes there, a swarm of them in 20 years.
Be awesome.
With a phased array of light lasers. And actually, I was just watching the Cosmos today, and he reminded me that the sensors would be like a gram, and it would have like a full HD camera to take pictures of this planet it flies by, all these sensors, radio waves, and whatnot, ranging. And you'd launch like 10,000 of them, because it's like frog theory. You know, most of the frog eggs get eaten by predators, and a few squeak by. So you have these like sails that are like a meter in diameter, with this tiny little 1 gram like chip. And you have this phased array powered by a freaking like a series of nuclear reactors, not even just one nuclear reactor. And you just launch them into orbit with a regular rocket, and then when they're sitting there, you just blast this super bright light at them, and they get up to this 20% the speed of light, and in 4 days or something like that, and that's their top speed. And then they get to Alpha or Proxima Centauri rather in about 20 years, and then plus 4 more years for the light signal of whatever they discover to get back. 24 years after launch, we have pictures and data and telemetry of what's actually orbiting these stars in the Proxima Centauri system. So yeah, it is a little tangent there, but Steve, you got me onto that tangent.
No worries.
But let's look at this. So 1.8 Gs, I don't know. It might be uncomfortable at first, but like Steve said earlier, you adapt pretty quickly. It's not that big of it. It's not that.
You acclimate. Sorry, biologists out there. They'll get me. That's not adaptation. That's acclimation. Yes, you're right. Biologists out there.
So ship time 2.4 years to Proxima Centauri. Less than 2.5 years. Come on, man. You can go there and back twice and get a bachelor's degree in physics in that time. Milky Way, the Milky Way's diameter, 13.2 years. Andromeda, 16.5 years. And then anywhere in the observable universe as it appears to us right now, in less than, or just a little over 2.5 decades. You leave when you're 22, you're still a sprite, youngish, middle-aged man or woman. Or whatever age you'll be when you stop and you say, okay, we've gone far enough. Like billions and billions of planets at your fingertips, even just between us and then the next 2 galaxies in our local group, 2.5 million light years away. That's 13 years. And again, you get there, everyone on Earth is gone. The Earth itself is gone, or everyone you knew is gone, depending on how far you've gone. The faster you move through space, the slower you move through time. And once you get up to like some critical threshold, whatever that may be, and you spend the overwhelmingly vast majority of your trip like practically frozen in time, then you're essentially you're moving almost not at all through time. So let me show you this. If we have here, so here's the Lorentz factor for just 84% the speed of light. Let's do 9, which is a speed you will be able to reach. If you're just going at that constant speed, 99 point all those 9% the speed of light, your Lorentz factor is, here, let me get scientific notation here. 22.4 million. So you're for every second of time that passes, like, in a proper time, only less than like 1/10 of a microsecond will pass. So that, you're like frozen in time. So like time is passing for you as you perceive it at a regular rate, because everything about your inertial frame of reference is time. Your neurons firing, the atoms in your neurons, everything about everything, all the physics is slowed down. That's why they call it relativity. Relative to someone at rest, it's slowed down. But because you're like the fish in the water, you don't notice. Everything seems normal. And then you get across the universe in your own lifetime. You're like, I must have been time dilated. And with that, I'm done. I'll take questions or comments now.
Yeah, I'm sure there's some questions out there. I told people to kind of put them at the end. Yes, actually, Dr. John Kroon does agree that 0.99 repeating equals 1. Out there, nerdy. he's pretty adamant about that, as I am. So that's something we definitely both agree with wholeheartedly, to say the least. We find it. I don't know about you, but I find that to be very a litmus test, I guess. If somebody kind of be able to understand objective math to the point where they're just trying to deny facts and actual proof, then yeah, it's not somebody I really want to have a conversation with.
Yeah. I agree there.
All right, so people had asked, let's see if I can scroll up here. One person asked about communication using quantum entanglement, which I think is prohibited, obviously. Information by quantum mechanics to be traveling non-local would be considered to be a violation, correct?
So yeah, I don't know if we'll ever get around that, but I do know in grad school I derived what's called the no clone theorem, which says that you can only clone reliably and transmit through quantum entanglement it's a weird number. It's like 5/6, and so because quantum entanglement is a random process, and so you can only I amend my statement. You can only prepare an identical quantum state in a copy sort of format through quantum entanglement with an accuracy of 5. So 86% isn't going to give you a very helpful conversation, and that's different than quantum entanglement through communications. Right now, the Chinese are beating us in sort of building a quantum internet, but what they've only been able to do, and because as far as we can tell, this is only what the laws of physics allow us to do, is to quantum entangle your encryption key, or your half of the encryption key, to your recipient on the ground. They've done it from orbit to ground-based receivers, and then the actual information can be transmitted classically after a much more robust and uncrackable encryption key has been sent.
That's more of a security thing than anything else.
It's more of a security thing than it is a quantum communication thing.
Yeah, that'd be very similar to like a Vermin cipher or something along those lines, where you're just worried about it being uncrackable. And I do believe that a quantum system like that would be something that is uncrackable, right? The only way to actually crack something like that would be getting inside the system. But if you get inside the system, it disturbs the system, and the key is no longer valid.
It destroys. It's like that Da Vinci thing where it has the vial of acid in there.
Yeah, exactly. If they try to get into, they would see the file gets destroyed, the information is no longer there, and so it just is. It's considered to be uncrackable. But as far as like setting up those systems, when did that system have to be set up prior to even going out in outer space? You have to set up something prior, as far as the encryption key and all this, but it still doesn't allow what we would want as faster than light communication, right? If I want to know what's instantaneously going on somewhere, like let's say we have a space station around Jupiter or something like that, and I want to know instantly what just happened there. There's no way to communicate that even with quantum, correct?
You need subspace transmitters, and I said earlier, if they're even possible.
Well, let me ask
but that would get the job done. Then.
Yeah, of course. And let me ask you, I'm kind of curious your position on this. As the way I understand it, and again, this is my way I understand it, but I hold that Minkowski space tends to be 3 dimensions plus 1 temporal, and then I hold that Neo-Lorentzian would be 3 dimensions plus 1 temporal dimension, while Minkowski puts it as more of a space-time, like more of a 4D approach, right? Would that be?
I don't see why not.
Okay, so if I have 4 dimensions, right? If I have only 3 spatial and 1 temporal, those are what I'm limited to, right? I don't know what it would mean to like go into subspace, because you're going in a direction that I don't know what would be to get you there. Does that make sense?
Yeah. Well, yeah. Right now, in terms of legitimate science, that's pretty much where we stand. But science fiction says you have this like phased array where at a certain frequency of this like Higgs field, you like turn off space. So like, because space we're thinking is an emergent property based off of entangled virtual particles. It's not actually just like an absolute fabric that's just always there. Actually, A Wrinkle in Time uses this same idea where you emit this like pulse at a very, very high frequency of a field that's non-electromagnetic, and it's something else. Like, let's just call it like a Higgs field. Do you think time is emergent? And you, Oh,
I didn't mean to interrupt you. I thought you were done. Do you think time is emergent?
I'll get back to that in a minute. So you emit this phased pulse, and it sort of cancels out, like destructively interferes with the wave function, like the exact like random signature of virtual particles that populate space-time, and it sort of dephases what would otherwise be an emergent property that we perceive as space-time. So it makes it so that everywhere in the universe is zero distance away, and they just like take a step to the left, turn the machine off, and they're on the other side of the universe.
Yeah.
Like that's a wrinkle in time, and that would be like that would be even better than zero space, because zero space uses a little bit of a different concept. But you asked me if I think time is an emergent property. I think even though time and space are intimately tied together, and that's a very Einsteinian like view, and I definitely lean Einsteinian. I got a poster up on my wall of him. I would think that time is somehow, because of its connection to like the second law of thermodynamics.
Mm-hmm.
I think it's fundamentally different in some way we haven't realized yet. And I've even seen a paper on how trying to reconcile time with thermodynamics. It coins the term of space and time as an emergent property, derivable from first principles, based solely upon considerations of statistical mechanics and fundamental laws of thermodynamics. And he actually uses a holistic, a probabilistic approach to derive Newton's law. I mean, for goodness sake, even Newton's laws were derived from first principles from this guy. I forget what his name is. I found it in college and I archived it somewhere. And apparently it hasn't been debunked. It hasn't received negative criticism. Last I checked, which was only about 3 years ago. So to answer your question, no, I don't think time is an emergent property of the universe. I think there's something sneaky about it. But then again, we think of Lorentz transformations as vector rotations in the space-time world lines graph with respect to the light cone, and you realize that you're just like space becomes time-like and time becomes space-like, and so they're kind of interchangeable, like matter and energy. And so there might be something about time that's fundamentally different from space, but not so different that they're not still intricately related. And we might find out in the future that if space really is an emergent property due to entangled virtual particles, then time might be produced along with it. In fact, at the quantum level, this might be why particles don't obey locality. Because they could be in two places at the same time, because maybe time is so fractured at that level, almost like space is so chaotic, and like the quantum foam and whatnot. Maybe time is like the quantum foam, all disjointed and chaotic and almost like boiling water, and then out at the macroscopic level it appears smooth and continuous. And maybe that's the source, maybe that's the cause of particle quantum non-locality. I don't know if you've ever thought about that, Steve.
Well, yeah, it sounds very familiar, like what they call the one electron universe, or one electron universe. Is that the name of it, if I remember correctly?
Yeah.
Yeah. So basically, there's one electron that actually exists, and everything is a manifestation of that one electron at different points in time and space. It's almost like if in philosophy they would call that almost like a universal that exists, like the color blue is an instantiation of an instance of one universal blue that exists somewhere. Then you have it poking out somewhere, basically as a property on something that's blue. So if that's the case, then it seems to be like we have a very coarse, granular understanding of what the universe is, and something is underlying that at a much more fine structure that we just either A, haven't been able to determine yet, or B, might be outside of our epistemic limit to do so. I mean, we're talking about such a granularity on the Planck scale that what would it even mean to have differentiation there? And as you said, yeah, if something fractures and let's say that this exists at all these multiple places in space and time. It would be interesting to think, what is that underlying reality, right? What is the fundamental that we may or may not even have access to, or be able to have access to?
Have you heard of the hypothesis that EPR equals ER?
Yes, the Einstein-Pulaski-Rosen.
Yeah, the Einstein-Pulaski-Rosen, the quantum entanglement effect equals the Einstein-Rosen bridge wormhole, and that quantum entanglement And if EPR if it really actually ends up being proven true, then we have just stumbled upon like a quantum theory of gravity that connects GR and quantum mechanics,
That
and then
would be
we
really
could
helpful for loop quantum gravity.
We could rule the galaxy. Hopefully, we'll be benevolent though.
Do you? So I know we went way off topic, but this is fascinating. Obviously, general relativity doesn't satisfy everything. Clearly, it doesn't play well with quantum. Do you think that what's going to pan out more, something like loop quantum gravity, or a modified relativity?
That's a good question. I don't know which one is going to pan out. Maybe none of them.
Yeah, well, I agree. Right? Who the hell knows, right? But they're fascinating the way they're approaching it. I think it's amazing how they're willing to say, "Hey, look, we may have to modify some shit here," just like Newton's theory may have been modified. Doesn't mean the theory is wrong. Just means it means some modification. But yeah, with the EPR equals ER, and that as you being an astrophysicist, that would have major implications even as far as like black holes and singularities in black hole and closed timeline theories. So yeah, I happen to like that kind of stuff. I'm fascinated by it. But man, did we go off topic? So we're going to try to bring it back in for questions here, if that's cool. Yeah.
I was hoping this stuff would inspire such discussions, but now we'll go back.
Dude, I just make shit up as I go along. You know that. Leo, question for John: has he read Sean Carroll's book, Something Deeply Hidden? What does he think of the Evertanian foundation of quantum mechanics?
Sean Carroll, I know the guy, not personally. Sean Carroll's book, what's it called?
Something Deeply Hidden. I have not heard of it even.
I'm writing this down. Hold on. I have not read it. Something Deeply Hidden. That sounds like right up my alley.
Did you ever read Davies?
Huh?
You ever read like Paul Davies?
No.
When growing up?
Well, maybe. I'm bad with names.
He used to write books on like how possibly we could like have FTL type things, like having a long, rigid and infinitely rigid. I don't know how this would actually happen, but an infinitely long, rigid cylinder that's spinning that would have frame drag that would allow time travel. But again, he's positing things that yes, in theory, if it was possible to have a Wizard designator with no distortion, sure, but that's physically, I think, is something that's prohibited by the universe, right?
Mm-hmm.
Yeah. So I mean, even neutron stars clearly have deformation to them because that's you have quakes on the crust, and that's about as dense as you can get. I mean, what's more denser than neutronium for the most part? I mean, if that even that has some malleability, minimal, and it's not a perfect rigid body, then what would be a material for a perfect rigid body? Is it possible?
Yeah, good luck. Maybe Costco has it
right?
because they have everything you need under one roof.
That's fun to think about, though. What would be something that could be even close to a perfect rigid body if even you break it down to just having neutrons and you still have some minor. I mean, what is it for like a quake for a neutron star, man? It's like a millimeter. It could have massive amount of energy released, right?
Yeah, if you drop a marble from like a foot off the surface, it will hit the surface going a third of the speed of light.
That's crazy, man. And I know you're a genius, but you got to admit, even you to wrap your head around the amount of power that is for a simple marble is pretty miraculous, isn't it?
Yeah, so 0.15, let's just say,
that's
like 0.08. I'm going to calculate this
the amount of power that would be, amount of energy released.
Yeah, so let's do this.
Just dropping a marble down because it's so compactified. It's so amount of mass into the small unit area that is so dense that you're just having huge amount of gravity.
Yeah, so that's the mass times c squared, 9 e to the 16.
The next time I have you on, you should do a presentation, and I've done this before myself, and I know how easy it would be and be trivial for you, but it'd be interesting to show people what the Schwarzschild radius would be for something like the lines of a white dwarf to a neutron star to a black hole. As you keep getting collapsing more and more, where do you reach the point where you're underneath a certain limit, right? Or when you reach that point where you've actually become a black hole, I think would be fascinating.
So yeah, the Schwarzschild. Whoa! Hold on.
What'd you break?
Okay, so Schwarzschild radius. So it's the mass over m sun times. What the heck? Why did I draw an S? I was trying to draw a 3. It's been a long night. 3 kilometers per solar mass. So if the Schwarzschild radius for Earth is like the size of a pea, and something like this, Mount Everest has a Schwarzschild radius of like an atom or an atomic nucleus or something like that.
I came up with 2.95 for the sun when I did my calculation.
Yeah, so I'm rounding up a little bit.
Yeah.
And then there's the gravitational time dilation factor, which is it 1 minus r over rs squared. I think it's 1 over that. Shit, it's been. I could derive it, but there's a.
I know, but it's fascinating because the way we'll have to work on for our next presentation, if you don't mind, if you want to like show the audience. Okay, if you have this much amount of compactification, you end up with neutron degenerative pressures on a white dwarf. You go further, you hit the limit for the neutron star, which is the Tolman whatever the limit is, the Tolman left limit. I don't remember this for a neutron star, but then you reach the Schwarzschild limit for the black hole, and it's like each time you get more and more compactification for electron degenerative pressures and neutron degenerative pressures, and I think the audience would eat that shit up, man.
Yeah, we could.
I love that stuff.
We could try something like that in the spring.
Yeah. Man,
Steve,
that's when I know something and I cannot think of it.
Steve, can you Google? I gotta Google this, or maybe we could put it in the description of the video after we sign off, because it's just killing me that I can't remember.
Yeah, is it the MVP limit or something? Well, man, I'm driving me nuts, man. Oh well, we'll figure it out later and get back. Oh, I know what it is. Tolman Oppenheimer Volkov limit. How could I forget this? I always forget this. TOV. Tolman Oppenheimer Volkov. Okay, I can never forget this, guys. If I forget it again, do something bad to my channel or something. But it's the Tolman Oppenheimer Volkov limit, and that's the limit for a neutron star. But yes, thank you, Leo. Remember, thank you, Leo, for pointing that out. But I looked it up first. Google.
It is a 1 over square root of 1 minus r over rs squared. That's what it is. So it's this squared.
You know what I think we should do? You might have a stream with Cheshire and Dapper Dino, and I know you hate the warp stuff, but it actually does relate to Star Trek in some ways that you can use what's called the Lorentz factor to factor in. Okay, if you're going warp 8, how fast is the speed of light you're going? There is a relationship there. And they did base it on some kind of science. And so what does warp mean? And it might be interesting. I mean, I know, again, you don't really like that approach.
No, I don't not like warp. I just feel like there's so much more potential in this way for good science fiction than warp. And as a practical application, it's more plausible to be realized nearer in the future than warp would. That's all I'm saying.
Yeah, I think you're totally right on that. Absolutely. Let's see here. I'm trying to go. If anybody asked any questions early on I missed, I apologize. Leo says,
Steve,
please let John know he's a good speaker. I don't know if he teaches, but he could, and you have taught, actually.
I'm teaching now. Yeah, I teach all the time. This is my 7th year teaching university physics and astronomy. And if my students are watching, how you doing? See you in class Friday. I do a Monday, Wednesday, Friday.
Homework students.
2 lectures. Yeah, homework is due Sunday at 11:59 p.m. And so make sure you're working on that. I might give them extra credit if they watch this.
I tell you, when I was in school, homework was my bane because I was like, hey, this is my free time. I don't want to do homework. And if I would have had Google back then, I would have. I mean, I still was on Dean list. I had a 4.0 in college, and obviously I graduated nuke school, but we didn't have Google back then. I got to tell you, don't you think that your education would have been a hell of a lot easier having the tools at your disposal that you have now 20 years ago?
Yeah, that would be awesome.
Right? I don't think people realize how fortunate they are to have so much availability of information. I don't know if this is probably before your time, John, but back in the day we had these big buildings called libraries. And they had these weird things called books. right? And they had paper from trees actually, and people would write in them, and you had to go like check it out to learn something, right?
Well, even in college, I'm talking like 2006 to 2010. I was in the library all the time. We had a great one, the Carrier Library at JMU, Go Dukes, James Madison University, and I would check out a stack of books
Right?
and pour through. Because you know what's cool about a book? It doesn't lose a signal. Like if your Wi-Fi is spotty or it's loading a page, or you Google something and it gives you like 6 million search results and the first half of them are ads. Come on, give me the
books,
book.
yes.
I want a piece
not
of
just
paper.
for that, but it's easier to find stuff. I can bookmark stuff,
Exactly.
I absorb it really much easier on a book than I am. Well, a PDF is very similar, I guess, but like you said, there are issues. But I like a hard copy if I can get it.
Yeah, I'm an old-fashioned guy like that too, even though I'm young-ish.
All right, let's see here. Let's see if there's any last questions before we start wrapping up here. Leo said, many thanks to Steve McRae for setting me up with him. I guess you and Leo have been talking. Leo Fellis, he's really into quantum mechanics. He's doing a video, I guess, on eigenstates coming up.
Oh, cool.
Interesting. Because I believe the first to admit, I never really got into eigenstates. And while I understand the underlying premise, I can't do any kind of manipulations with them or tensor like that. There's nothing I really got into, but I'm fascinated by it. I am fascinated by. I've had simple matrices, but to really get into it and learn about eigenvalues and eigenstates, which is something that I never dived into, and so I'm definitely gonna be watching that video from him.
Yeah, I'll check it out too.
Oh, he's talking about his debate with Robert Sungenis. I'm sorry. Yeah, you're welcome for that, Leo. Yeah, so Robert Sungenis, I don't know if you've heard of him, John, but he's a you're gonna hate this. He is a geocentrist that believes that the entire universe rotates and revolves around the Earth.
Well, it doesn't. Well, then it doesn't. Well, then here's what I have to say about that. It's not just revolving around. It's also going in all these weird epicycle movements. It's going to revolve around us, but like for no reason, go like this and that. And there's going to be also the 26,000 year wobble due to precession. That's obviously not the Earth precessing in his view, but the universe just randomly has all these epicycles upon epicycles encoded into it for no reason. And somehow the entire universe, how massive and huge it is all doing these complicated rotations and epicycles all as a single rigid body. Wow.
Yeah.
What a
I would put it the same way. As a matter of fact, it's kind of funny that the way Sungenis approaches it would not be something that is physically prohibitive, but it's non-parsimonious to the extreme.
I would say it's both of those.
I don't know.
Yeah.
I don't know. I would have to think about that. How actually?
So galaxies 13 billion light years away in Hubble's ultra deep field are actually they are conforming to Earth's motions, according to this guy.
Yeah, but couldn't you just change your origin and your frame of reference and say instead of like we're going through some kind of proper motion through the universe is just centered around us, and change your frame. That would just be simple transformations, wouldn't it?
No. Not at all, because the universe is huge. It's not even in the same reference frame. Like you're looking back in time, and so you violate causality just by having a universal geocentrist view. Mm-hmm. You violate it just right off the bat. Forget about observations. For that, then? It's literally physically impossible. It's not just parsimonious to the extreme. It violates.
Like far as like materialistically, physically, I don't think it would happen either. But I'm just saying, as a frame of reference, you could make the equations kind of work out, couldn't you?
No, I don't think so.
I don't know. He tries. He works with a guy named he was the producer for that movie, The Principal, Rick Delano, and I've had both Robert Sungenis and Rick Delano on before. If I did, wait, who did you have a conversation with on the Non Sequitur show? Maybe did you talk to one of them? I don't remember.
Yeah, it was the truck driver guy, the flat earther truck driver. Oh, the Plain Truth, PLANE.
Oh, that what it was.
Truth.
Yeah, I had both of them on before. Actually it was Carrier that I had with one of them. I remember that. Me and Carrier, Dr. Carrier, had gone against Rick Delano, and we're just like going, what the hell is going on? It was weird, because obviously we're not geocentrist.
I would like to see what you guys say to such a person who thinks that the universe revolves around the Earth magically.
Well, you know what's
and
funny?
with,
I'm
no
not even fronting. We finally got it boiled down to a simple thing, and I'll tell you what the simple thing was. He finally admitted, he's like, well, the reasons for this is because God said so.
No, he didn't.
We finally got it down to distilled. Well, because God says this way, that's the way it has to be. Because I had been explained to him, look, the physics doesn't show this, the science doesn't show this, the math doesn't show this. So what is your justification for why it is this way? And he's like, well, because God. And I'm like, that's not a scientific justification. You can believe that all you want for a theological point of view, but it's not. You as a scientist, anybody as a scientist can never posit God as an explanatory thing for something. That's not what science allows. And so for him to do that, he just took the entire conversation out of anything science-based, which he came on the show to talk about. Science, right?
Yeah, I agree there, but I would go so far as to say Dr. Ross could even tell him that the scriptures, the Bible doesn't even say that. Yeah. Like, that's a really childish, juvenile, like, mundane, anti-science interpretation. Absolutely. And never even implies that. I don't know where the hell he's getting that from.
Well, I mean,
not in the Bible.
Like I said, he is a geocentrist, man. So they're like young Earth creationists, only worse.
So yeah, those people, they got science wrong and the Bible wrong. They're just completely flat out wrong about everything. Must be.
So would you call that fractally wrong?
Yes.
Wronger than wrong. That's how I would call it. Yeah,
very.
Ross believes that he believes in the book of nature and the book of scripture, and he does kind of accept non-overlapping magisteria, and I'm fine with that. And I got to tell you, I have the utmost respect for Ross because as somebody with very strong religious beliefs that he has, he still respects the sciences, and he's one of the nicest guys you ever want to be in your life. He's very kind, very generous, and those are the kind of the science theists that are out there that I respect, right? I mean, so they're not putting out misinformation for science. I've read some of his books. Problem Planet was a very good book, but I respect him immensely for that. He's just a really kind guy, man. I don't know if you've ever had a conversation with him, but you guys would.
Yeah, I had a podcast with him.
Oh.
Him and someone. What was it we were doing? We were. I remember the lady said, "I appreciate you all for being very respectful." We were talking about something.
Can you move it? By the way, people, Jess wants to see that beautiful face of yours. If you can move it down, your camera a little bit down, or there you go. What? There you go. Yeah, there you go. Oh, he smiled for you, Chesh. Look at that. Smiled for you.
Oh gosh. I didn't know she was on here. I thought she was just in the.
No, she's in the live chat. She just said, "Can you help John with his camera?"
I'm just sort of slouching.
He looks like he's my height. No, John is like nobody's your height, Chesh.
It's just getting really hot in here.
Yeah.
And I have my door open so I can let the snow in.
But I don't think anybody's got any questions. But man, this was awesome, dude. It's been a while since we were able to like hang out, and I miss it.
Yeah, I've been wanting to do this exact talk for about 2 years since just after I met you. I remember talking to you about that.
Yeah, no, absolutely. And I'm sure we'll have plenty more. People have any suggestions, let us know. I like to do presentations very similar. You're a lot more in depth, obviously, but I mean, I like to pick a topic and go, hey, look, if I can explain it in a layperson, then somebody can understand it. So maybe people have some suggestions where we can maybe both kind of like do a little cooperative presentation of some kind, like I've done with Landon before.
Yeah, I want to get back on DEF CON science with you and Landon sometime.
Yeah, we want to start that back up. He's been really busy. It's funny because a lot of the shows that I do are just time things because Landon has been really busy, so we haven't been able to do DEF CON 1. I do Over and Under with Chris Attlee, but he's been really busy. I do Caffeine Corner with Chesh, but that still happens on Mondays. And so, it's just life stuff, So, but yeah, I'd love to have you back on with DEF CON 1 Science with Landon, and I know maybe do something on. You know what I would love to do? If we could do something on electromagnetism or like Maxwell's equations, I would be like thrilled to death. Because I can't make it past like the first one or two. I just can't. I get for one easy, and two, I can understand. But after that, I'm like, magic. It's just magic.
Well, Steve, I'll do that if you let me on the caffeine corner, so I could chat with you folks.
Yeah. Pick. What do you want to talk about? Sure, you can come on the caffeine corner.
No, just like a secondary character. You guys do your own thing, and I'll chime in.
How about we have you on for a caffeine corner for a call-in show one of these days?
What's the call-in show?
I don't know. We'll pick a topic. We'll figure out something. People call in. They get to ask you questions.
Oh, Colin. I thought you meant Colin. Some guy, Colin.
No. Some people call in.
Call in. Yeah, dude. I would love to be a part of that. I'll hop on sometime, have some coffee or tea.
For me. Yes. By the way, people didn't notice that is actually really John's mom out there. Yes.
What in the world?
Yes.
I can't see. Can I minimize this yet?
Yeah. I can take this off. There you go. Okay. Yeah. Now.
Okay.
Yeah, because your mom has been around before.
Yeah, she's silly.
Yeah. She should be very proud of you.
Yeah.
So just want you to come hang out with us. We'll arrange something. But this was awesome. I do appreciate it. My fans appreciate it. My subs, fans. If you want to be, I know that's going to make some video. Steve says he has fans. I don't know what else to call people. People that like my shit. I don't know. You know?
Yeah.
But I think that people enjoy these types of discussions, and I think they like learning. And I think that when they have somebody come in and go, hey, look, this is how this works, they go, oh, man, I get this. Or if they don't get it, they go, maybe I can ponder this a little bit. And later on, something clicks with them, right? And that's how it works. I mean, a lot of stuff I didn't get right off the bat. I was like, I don't understand any of this. And it's like, okay, I have to go do some reading and then have it click for me eventually,
Yeah, you got it though. You're one of the sharper ones though.
No, but it takes me a while. This is what I'm saying. There are people out there that just naturally have a predisposition for learning this kind of stuff, and I've known many of them. You're one of them, and few people I just envy because it's like they understand it a lot more intuitively or just naturally, and it for people like me, it's like I gotta like figure this shit out, man. It's just I'm not that smart. So. All right, but anyways, it looks like you got a couple fans yourself, so that's awesome, man. I know Leo really appreciates this stuff, and Leo says that you didn't ask a question on the Evertanian Foundation, but I don't think that we knew that was. Oh, he's talking about the many worlds interpretation, but we'll get into something like that later on.
Yeah,
it's a different thing. But all right, guys, thanks for watching this. Dr. Kroon, you're always welcome on anytime, and I miss talking to you, man.
I miss you.
But get some free time, hit me up, and we'll just talk off air.
Just
chat,
hang out. Catch up, yeah. All right, thanks, man.
Good night, guys.
Good night.